I do want you guys to, if nothing else, to take away from this course the idea that science is supposed to be skeptical. Like, you're supposed to not trust the things that you read in the textbook outright. You're supposed to think about them. When you read a report, even when you're a scientist, and you read your colleagues' work, you're supposed to be skeptical. You know, there's this really great quote from Feynman. Richard Feynman was like a very, like one of the most beloved physicists of all time. Heavily mathematical dude, but he said, science is the organized skepticism in the reliability of expert opinion. And I think that's a really healthy way to approach science, right? And I want everybody to come away understanding that we need to be skeptical of our own ideas. We need to be skeptical of the ideas of even the best people in the field, because ultimately science progresses. It always progresses. We learn more things. We come up with better ways of framing the evidence that we already have. And this is getting a little bit lost in our culture and in our civilization, and I think it's really, really critical that we come to understand what we're doing when we do science. We're not trying to write textbooks in stone. We're writing them in a way that can be constantly updated. Questions about that? Super important. And so I'm going to keep bringing in strange ideas and contradictions that appear to me as I go through this material. And I'm not saying that those ideas are any more correct than the ones that may be there in the first place, but they are interesting kernels to chew on. And there's so much work to be done. If any of you go into any of these fields, and I hope you will, because it's a really fun, all these are really fun topics. There's so much work to be done. And I think that's really exciting, and it's really the opposite of the way that I felt when I went through college. I kind of felt like everything was sewed up, and there was just some details to iron out, but it's not like that at all. Questions? Okay, cool. Well, today we're going to finish up the astrobiology, like I said, very quickly. And then I want to mostly talk about exploring the moon. Your textbook and quizzes are largely about the moon and its composition and so forth. We'll talk about that. I did a lot on the moon earlier, a few weeks back. So we're not going to bother with the origin stories. We kind of went through that already. But I do want to talk about how we are starting to approach exploring the moon again, because we haven't been back in a very long time. We went very briefly, and we haven't been back since then. And now all of the same processes are ramping up, and they're being improved upon. And there's all sorts of different agendas about what's going to happen and how it will be, how we'll treat the moon. And so I want to talk about all that today. I think that's mainly what we'll do. And then at the end, I want to talk a bit about Mercury, because Mercury is a planet that looks a lot like the moon. And ultimately what we're doing today is we're opening up our discussion about the terrestrial planets, of which the moon is considered a member. It's an honorary member. Of course, it doesn't orbit a star, so it's not technically a planet. But it's very similar to Mercury, with some really interesting differences. And the way that we approach understanding the history of both of them can work hand in hand. So I'm going to try really hard to make it to Mercury by the end. If not, we'll get into it next time. And of course, we'll move into the terrestrial planets next time, like Mars and Venus. We've done enough on Earth for this course, I think. Okay, cool. Also, I keep saying we're going to get to the sun. If you take the next semester, it's going to be all about the stars and how they work. And so we're not going to get to the sun until next semester. Apologies, but it's just too big of a topic, and understanding stars is an entire branch of science that really requires its own semester, at least. So, cool. Let's just wrap this discussion about biosignatures really quickly. So there are obviously molecules we can look for if we go to the surface of a planet. There's the lipids and carbohydrates and nucleic acids that we're familiar with on life. Those will be nice if we can find them, but it's highly likely that those things will degrade and disintegrate over time, so that's not really our best option. However, it also requires us to go to the surface of a planet, and like we talked about, getting out all the way into another star system, let alone a star system that has Earth-like planets, That's quite a project, and that will take many, many decades, if not several generations, even in spaceflight. So one thing we can do, which is kind of cool, and you might have discovered this concept if you've taken any basic chemistry, is there's this idea of chirality, right? So molecules have this symmetry, and we refer to it as a handedness. And so organic molecules can have a right-handed form or a left-handed form. And if they're not associated with anything living, that is, like if these compounds are just being formed through geologic processes, we generally find a nice mixture of the two right and left-handed forms. However, in biological systems, you really see a homogeneity depending on the molecule. Like amino acids in your body are all left-handed, whereas the sugars that you use are all right-handed. And so one thing that's really cool about this process is that you can look at the way that light interacts with these molecules, and you can read the handedness of it as a result. Because what happens is that light can be polarized in a fashion such that the waves, the deformation waves that are associated with light, called light waves, light frequency, they don't just necessarily travel randomly. And in fact, we can use different polarizers to make sure that those waves are all lined up together. And then what happens is when you have this polarized light and you shine it on one of these molecules, they're going to alter the path of that beam ever so slightly in a way that you can read out, which it is. So this is something that we can do remotely, which is really promising. And there's a lot of hope that once we identify some of these Earth-like worlds, we'll be able to apply these methods and dig in a little bit deeper. This is just, so I should have shown you that earlier, but this is essentially the concept of rotating the polarization of light. So there's a couple other things we can look at. We can look at isotope ratios. It turns out that life really likes using lighter isotopes than in chemical elements. Those are the ones with less neutrons. And this is something we can also get through spectroscopic analysis, because different atoms, depending on their weight, are going to have different absorption profiles. They're going to have different energy states in their shells as well. So that's really cool. And then there's just this cluster of molecules that we should expect. You know, obviously we're looking, this is a little bit of a confusing diagram, but bear with me for a second. It makes a bit of sense. So all these molecules that you see, like look over on Earth over here. There's obviously oxygen, molecular oxygen, which is absolutely essential for our purposes if we're going to go out and make home on one of these planets. We should also expect to see some molecular water in the air, some carbon dioxide, and then ozone. But there's some problems, and then there's some other things we should not want to see, right? We don't want to see a bunch of carbon monoxide out there, right? That'll choke us. Carbon monoxide is actually it's very similar to oxygen in size, except it's a lot more polar. So when it binds to your hemoglobin in your blood, it won't let go. And that's a big problem, right? Because you need the hemoglobin to transport oxygen. And so we don't want to see that. And, you know, there's other toxic chemicals too. We don't want to see a ton of methane in the air. But there's some problems too, right? This tetraoxygen compounds, this carbon monoxide, carbon dioxide, these have other means by which they can be generated that aren't necessarily signs that there's any kind of living going on. Obviously, we think of carbon dioxide as being generated during photosynthesis. There's other means geologically by which it can be generated, and the same goes for methane. So different combinations of rocks and precursor chemicals can lead to the production of some of these molecules, and they give us false readouts. So there's really only a few that we can look at, and we have to ask ourselves questions about the ratios of these chemicals and how they could be misleading us at the same time. And then once we get out there, we can look for microfossils. This is a tiny little organism the scale bar here, I believe, is 2 microns. These are pretty tiny. They're not quite as small as bacteria, but they're very, very close. And we might be able to see something like this. This is from the deep sea drilling program. But again, we have to get out there to see such things. There's also the idea of scanning the radio waves. So I want to briefly mention the SETI project, which has alternately been well-funded and defunded. Right now, you can go and donate processing power of your computer if you want to. They're crowdsourcing processing power because they have all of this information coming in, but they're not able to sift through it. And back when SETI was really well-funded, they were sorting through it by hand. And there's this very famous moment where a scientist noted a very unique pattern of coherent information that came across the radio waves, which is famously called the wow signal because he wrote wow next to it. They weren't able to redetect that, but it still, like, to this day remains a very intriguing instance of something that could signal that there was an intelligent life form trying to get in touch. I think that there's just not much effort going into this kind of thing right now. And so this is something to think about. I really think that it's worth contemplating whether we want to be spending our money advertising to aliens or whether we want to spend our time scoping out their signals. And it's probably better to understand them before we get in contact. Just my opinion. What else? Okay, so there's a couple of other cool things that we can look at, which are technosignatures, right? If there is intelligent life in the universe, in our local galactic system, we should be able to see signs of their machinery. And there's a number of really cool ideas people have for what the eventual future of a technological civilization would be. One of them is this idea of literally surrounding the sun with a structure, because the thought is that our civilization wastes a tremendous amount of the energy that comes out of the sun, right? We're a tiny little ball, and we have to wait for the sun to illuminate part of our planet in order to capture any energy. And so the idea is that maybe the alien civilizations have actually covered their sun, and we'd be able to see some sort of, artifact of that, which is possible. There's also the idea that maybe the aliens have figured out how to move their sun, which is really wild, and we would be able to see that. There's a really fantastic book called Star Maker that's a science fiction piece, but it's fantastic, and it explores, this is by Olaf Stapledon, and I really recommend that book. I should have pulled a screenshot of it, but he explores some of these ideas, and he actually gets into this whole idea that maybe the stars are somehow sentient and in communication with one another, and really cool idea. Okay, so that idea is called a Skadov thruster, moving your sun around. We might be able to see asteroid mining too, which is interesting. We might be able to see excess infrared radiation from the different spacecraft that are out there. And people are looking for these things, which is pretty cool. Satellites, magnetic sail spacecraft. There's all these little signs that we could see. And of course, just the trajectory of bodies moving that are anomalous, that don't seem to fit with gravity. And actually that Oumuamua object that came into our solar system recently was a good example of this. And that's a really fascinating one. Did anybody have a chance to read about that at all? Check it out. You guys got to look it up. It's weird. Okay. Very strange. All right, let's talk about the moon. So the moon has two sides. They're very, well, from our perspective, there's two sides, the far side and this side. There's no actual dark side of the moon. Sorry, Pink Floyd. It's getting plenty of light over there, depending on where it's at. So there's two basic features of the moon, and I'm going to explore them in depth after we talk about the exploration a bit. You have these dark patches, which are called Maria, and then we have these highland regions, which are a bit lighter. And they're going to come into the story about the age and the process of the evolution of the surface, and I hope that we'll be able to get into that a bit. We know a little bit about the interior structure of the moon, primarily from seismic studies, much like we know about how the Earth has different layers in its core structure, in its interior, because the way that vibrations travel through it depend on the material properties of the interior. And so there's some evidence that the moon, just like us, has a solid core. It has a really tiny liquid portion, and then most of the outer portion of the interior, the mantle, as we would call it, the cool region, dominates. And it's thought that in the past, this wasn't the case. It was warmer, and there was a lot more volcanic and magmatic activity, which is thought to have produced the dark Maria regions. So this is going to be interesting because I want to compare and contrast this to Mercury, which is essentially, looks a lot like the moon in many ways. The surface is very similar. But Mercury has so much core, it's almost entirely core. You know, Mercury and the moon are very similar in size, but actually the core of Mercury is almost exactly the same size as the moon itself. So Mercury is basically a core with a shell. And that's a really interesting thing to contemplate, especially when we're trying to explain why we have a magnetic field and nobody else does, none of these interior ones. Mercury has a really weak magnetic field, and so there's some thoughts about why Mercury has been able to maintain this liquid form, and we'll compare and contrast those at the end of today's talk. But, you know, people have been dreaming of going to the moon for 100 years or more. There was quite a bit of excitement. This is a little scene from a French movie called Le Voyage dans la Lune, which is actually really worth watching. It's a silent movie, but it's quite interesting. They shoot a giant bullet with people in it at the moon and have all sorts of hijinks. It's quite entertaining, just, you know, despite not being audible. But almost, and really, the idea of going to the moon seriously wasn't proposed until 1920 by Robert Goddard, who was an engineer and physicist. His name is carried by the Goddard Space Institute, which is basically NASA's science division. And he really kicked off this idea. And a lot of the technology didn't come online until actually World War II. We can thank the Germans for developing the rocket technology that we use to this day, essentially, which is quite an interesting story. You know, there's a lot of thought that if we hadn't managed to grab all of Germany's best scientists, maybe the Second World War wouldn't have turned out so pleasantly. And so we brought all those Nazi scientists over here to kick off our space program, and they were essentially the ones who developed the rockets that took us to the moon. And honestly, the rockets that we're using today to go back to the moon are not so very different. So that's a really interesting twist of history right there. I think there's something hopeful about that, actually, where it's like, you know, everybody wants to work for the good guys. Everybody wants to work for the people who are going to win. And so that was good. All right, but most of everything that we know about the moon, most of the definite hard evidence that we have has literally been collected in the last 50 years. So people's conceptions about what the moon was prior to the 1970s were just completely wacky and off the wall compared to what we think now. Everybody thought that the craters were volcanoes. People thought there would be life there for sure. You know, people see what they want through telescopes, and none of this was really laid to rest until we went there. So actually, between 1968 and 72, we put 12 astronauts on its surface, and we have unearthed pretty much all the information that we're going to talk about today. The Russians were actually the first people to get out there and take photos of it. They had a series of missions called Luna, as opposed to our Apollo missions. And then they actually landed on the surface with Luna 9 in '66 and took some pictures and some other data and brought it back to Earth. So, and they were really, really neck and neck with us in terms of, it was called the space race for a reason. What's kind of fascinating is they just threw in the towel as soon as we landed people on the moon, which I think is really fascinating. I assume that they were having economic problems and so forth too, and probably were looking for an excuse to give up. But the space race is back online today. There's a number of countries that are really neck and neck right now to get out there. China's got some landers on the backside right now. There's moon colonization programs from several countries, including the Arab Emirates are building a big space program. They're a very rich, tiny country, which is quite fascinating. So your textbook goes over the different missions that the United States pulled off. It's a very United States-centric picture of moon exploration, but I think it's valid since, to some extent, since the United States were the only country that managed to walk around on it at the time. And honestly, like the technological achievement and the amount of money that was spent on it back then is hard to fathom because they literally stopped at some point. There was a moon mission at some point. The 13th Apollo mission was a bit of a disaster. It freaked people out. The Vietnam War was raging. People were just kind of turning against the government and freaked out. So the plug was pulled on it, and nothing happened for like 50 years, which is fascinating. The interesting thing, though, is that it didn't really cost that much money to get it done. It was something like $100 for every American spread over 10 years. So that's like each person in America buying a pizza every year or something. But still, the public enthusiasm had dwindled for whatever reason, and we stopped for a long time. And now we're thinking about revisiting it. So in the interim, there was a number of robotic probes that were sent. We can see out here some different orbiters and impactors. Japan, Europe, like I said, China, really leading the pack there in recent years. And we learned a lot in those missions too. We learned about different accessible water ices, and we'll see how those are important for our future colonization projects in a minute. All right. So the goal right now is to build this thing. This is called the Gateway Project. This is going to be essentially a space station which orbits the moon. And so for all of the different planned NASA missions to the moon, which is called the Artemis Project, they all depend on the construction of this habitat. Because this habitat is essentially going to be the docking station. When we send rockets up there, this is where folks are going to stay at, and then they will go and land off of this. So the Gateway Project is going to be assembled over many years. Well, it's supposed to be done by 2030, but these people are always overly ambitious. And then, they're opening up this project to private contractors too, which will probably accelerate things even further. So most of the service components, a lot of these modules will be built by private companies and sent up there. And NASA is going to take a backseat role and essentially just administer the project and maybe deal with the crude parts and training the astronauts and so forth. Yeah, okay. So let's talk about that rocket ship a little bit. By the way, Artemis, we talked about, which is really interesting that it's come back up again. This story is just so pivotal to astronomy, the story of the bear in the sky. If you'll recall, Artemis was, in the Greek religion, was the goddess of the wild and the wild animals, and was carried over into Rome with Diana. And so this is interesting how we carry these myths forward even into our futuristic explorations. You know, what's the goal of this? Why do people want to go to the moon? It seems like NASA is largely motivating this exploration because they want to go to Mars eventually. And ultimately, they want to be able to get out. You know, our long-range goal is probably to find ourselves another home in a different star system. And so in order to make it out to Mars, we're going to have to build some huge ships. We're going to have to build a lot of resources. And it's very, very expensive to build things on Earth and send them out into space because we got all this gravity and we have this huge, thick atmosphere. And so if you want to get something into space, you got to cram it into a little tube and shoot it up through the sky. And that's a very, very expensive thing to pull off on Earth. However, on the moon, it's pretty easy. There's no atmosphere. Gravity is really weak. And so the thought is that if we can get to the moon and build structures out there, we can levitate them up into into a low orbit and assemble the big spaceships out there, which will eventually take us out to Mars and beyond. So the moon's thought of as this perfect way station. It's a staging zone for everything else that comes. And there's, of course, we'll get into this in a second, but there's a great deal of resources that can allow us to find the starting materials for all of the different metals and fuels that we'll need to pull those missions off. So there's some sense. It makes a lot of sense to do things out there. But this is the basic platform, right? We're going to strap everything to the front of a big rocket, much like we did with the original Apollo mission, and send it up into Earth orbit. We'll get rid of these rocket stages, and a small capsule will take us out into the moon's range. And so here's a picture of that little capsule separating, which will actually, just the little tip of it will be returning to Earth at the end. So this part that it's separating from is the module which will actually be orbiting the moon, which is basically the same thing that we had back in the 60s, 70s with the Apollo program. And that's what's really fascinating to me about this, is that we're essentially having to rediscover all of these tools that we developed very, very quickly back in the 20th century. And they're being improved upon incrementally, but it's essentially the same idea. I'm sure the technologies, as far as the computer systems, have evolved a lot, but the basic floor plan is the same. Yeah?
Why don't we use shuttles? Well,
yeah, a lot of people think we should. I mean, the cool thing about the shuttle is it's reusable. Yeah, so, you know, so I was talking about how great Richard Feynman was at the beginning of this talk, and he actually was the captain, or whatever it was called. He led the risk assessment team for the shuttle program. And he crunched the numbers and said there was something like a 1 in 10,000 chance that the shuttle would fail. And it turned out that it was quite a bit higher than that, because I think there was, I don't know how many, I think there was 7 shuttles made and 2 of them blew up. That's not a very good odds situation. And so I think that idea really ruined it for the public perception of the shuttle program. You know, and perhaps it was just freak accidents, but it didn't look good. But I've definitely talked to people who really love the shuttle program too. It's much easier to jump out there and work on things and grab a satellite, bring it in to repair things. It's much easier with the shuttle. I think also this basic rocket structure we have now might be a bit more efficient in terms of just getting things out there in the first place, not necessarily in terms of manipulating them. So you don't have much of a cabin, really, or much of a platform at all once you're out there, like we did with the shuttle. You had this huge cargo bay. You could really bring things in and manipulate them. But I think it's cheaper just to pack them into a tube and send them up into space in the first place. And of course, like I mentioned, the real goal of all of this now is to start doing the assembly in space, right? We're going to try to send as little stuff out there as possible. It's extraordinarily expensive to get things off the planet. But if we can do the work out there in space, if we can mine the materials in space and do all of the assembly and construction out there, it should go a lot faster and be a lot easier. Some of the spacecraft that we'll need to explore interstellar space are huge, the size of cities, right? This is just unimaginable to be assembled on Earth and then sent up there. When I was a kid, there was a lot of hope that we'd be able to construct this thing called a space elevator. Have you guys ever heard of that? Which is like essentially what it sounds like. You have a big long string up into space, a big long tether, and you just attach some sort of car to it, and you can zip things up into space. But it turned out that the materials necessary to pull that off haven't been fabricated to this day, and there's dwindling hope that we'll ever be able to have strong enough materials to pull that off. So the focus has shifted to outer space assembly now. The basic plan over the next 10 years with this Artemis program is to build something that looks like this. They want to assemble a habitat on the moon. That's what this little tube thing over there is. They want to make a very big rover-looking thing that actually somebody could live in as well, so they could travel across the surface to different regions. And then they're going to make a tiny little dune buggy again, too, like they did the first time. The real goal is they want to be able to get down and explore the southern polar regions where there's supposed to be a lot of water. And we'll talk about why that's important, but it turns out that you can make rocket fuel from water, right? So water, we'll get to that in a second. But let's take a brief tour of these different Artemis missions, because I think it's important for you to understand what you're going to see popping up in the news in the next decade. So the first one that they're going to do is something like a dress rehearsal. They're going to launch the spacecraft just as they would with a crewed mission, except nobody's going to be on it, presumably to make sure nothing goes wrong with all of the different nav and life support systems. And it's a dress rehearsal. So they're going to fly out there. They're going to briefly orbit the moon. They're going to check the different stages. They're also going to be releasing a few little CubeSats. You've sort of like Elon Musk's Starlink program, which will be useful for making different measurements along the way and relaying communications as we go forward and start to bring people out there. The next mission will actually put people on to the spacecraft. And it's going to do more or less the same thing. Instead of orbiting the moon, though, it's just going to do a little slingshot maneuver, which I assume is, again, just aimed at narrowing the risk and making sure everything works out fine. Nobody's going to land on the moon in this mission. It's just going to test out the flight path and test out the re-entry mechanism, which is always a little bit dicey. And then the third mission is going to be an actual crewed landing. So they're going to basically make use of the same rough concept that they used the first time they went to the moon. They're going to put this module into orbit. They're going to disconnect the landing portion of it and keep the other part of the capsule orbiting. And they're going to spend something like a week down there and do a couple of spacewalks, or EVAs, I guess they call them. You're not in space at this point, but some moonwalks. And so there's only going to be 2 astronauts who are going to go down on the little landing vehicle. So this is hopefully what we'll see happen this decade. The long-term goal is a bit more complex, but essentially involves getting down to the South Pole, trying to see about this water, getting commercial companies involved to get the payload delivery system ramped up so that we can get that gateway module assembled for docking and having ease of use and easy access to the surface. And then ultimately developing ways to get large-scale cargo both up and down from the moon's surface. So those are the bigger programs. This might take 50 years to pull this off. Maybe you guys will get to see some of that happen. Hope so. So a lot of the fuel for this is coming from the private sector right now, which is kind of an interesting moment in the history of the world. There's, Elon Musk and Jeff Bezos are pumping money into these sort of projects. There's also a number of billionaires who are trying to support the idea of tourism, and that's variably worked out. There's this one Japanese businessman, who is this guy's name? Daisuke Enomoto, who's paid something like $21 million over the last 10 years to get a trip on one of these private space company with one of these private space companies, and they denied him at the last minute because he had some kidney stones. And and they wouldn't give him his money back. And so, if the companies keep misbehaving like this, maybe they'll lose their investors, and this won't be such a boon for the whole project. But what else? I mean, there's another Japanese businessman, Yusaku Maezawa, who has bought a ticket on a planned SpaceX flight to go to the moon, where he wants to hire a bunch of different artists to travel with him for free. Not hire, sorry, he's going to pay for their tickets. And so there's a lot of people who are actually putting up their money to make this happen, and I think that could potentially drive business, drive the progress of this project, because the taxpayers aren't super interested in it. What do I want to say about this? Again, the whole idea is to not send materials from Earth to the moon, but to actually get them off the moon itself. One of the cool ideas is that once we start building things on the moon, we don't need to use rockets anymore. There's this idea, a concept called a mass driver, which is essentially a big catapult. And the idea, it's like a rail gun. The idea is you just have you can put your packages on a big sled and just sort of throw them off the moon really fast, which is intriguing. And it should be a lot less expensive than trying to make fuel. There's a lot of markets also for the resources that we find on the moon. And this opens up a whole can of worms about regulation of the industry out there, because there's no EPA on the moon. People can pollute as much as they want. No one's going to stop them. There's no atmosphere to capture the pollution, so it probably won't be an immediate problem to anyone, or a problem at all, maybe ever. And there's a number of really good, there's a number of different resources we'll get out of it. But I think that the main industrial pull is not from the mining itself, but it's from all the support activities, right? We live in we live with a service economy right now. Most people make money by offering some support to existing infrastructure. And I think it's going to be the same way with the privatization of space also, because all those different projects are going to need help that NASA's not going to be delivering. So, they're going to need somebody to make sure that the astronauts' equipment is all top-notch, that their satellites are all functioning, that all of the proper technological R&D is happening, that there's that there's good support for these projects based on Earth and maintenance of the different structures. And so all of these external commercial avenues are starting to open up. And these are the ones that you really see people investing in legitimately right now, because they don't have to necessarily build spaceships. They just have to support the projects from beneath, and they can pick up government contracts for that. They can recruit investors. It's going to be big business, essentially. Already, the satellite industry is huge business, and so the same thing is going to happen with the moon. And then there's also the mining of the moon itself, and this gets us into considering a bit about the composition of that lunar rock. We call it regolith. There's a fair amount of metals that we could use for our different spacecraft and so forth. Something like 14.9% alumina, which is an oxide of aluminum, calcium oxide, which is lime, another 14% of iron oxide, 9.2% magnesia, which is an oxide of magnesium, titanium, sodium oxide, basically all these metals that we would use for manufacturing strong, useful industrial metals, here on Earth are out there. And these are very expensive to mine on Earth, and they should be readily available out there. And that's that's really fueling a lot of the drive for people to invest in these projects from the private sector. The water, like I said, is also a huge promise of the moon. So the basic idea of the systems for propulsion that they're imagining for the Mars flights has to do with using electricity to split water into hydrogen and oxygen, which are two nicely combustible fuel sources, and they can be harnessed much the way that we do on Earth once you have them. So if we find water, we can make rocket fuel. And that is the huge end game, at least as far as NASA's looking right now for the moon project, is really being able to process all this water, which is mostly found in the polar regions. And for whatever reason, they can't land on the polar regions directly, so they're going to have to be explored using that big, look like a big RV type thing. So it's going to be a stepwise process of getting down there. And it's thought that, deep down there might be water within the rocks as well. And this has been explored extensively. The Indians, the country India, has done a lot of the work analyzing samples. They've sent a probe down there called Chandrayaan, which has examined something like 40 different craters. This is a series of probes, obviously. And they found something like 600 million metric tons of water ice just in these craters alone. So it's promising. We might be able to scale this process up before we get down to the polar regions. This is something of the distribution of the water, which you can see again is mostly at the poles. And then there's another interesting piece of this story, which is helium. Well, first of all, helium's an interesting story on Earth. We're actually running out of it. It's very light. You've seen probably helium balloons at birthday parties. And helium is really useful for cooling processes, especially for like super intense electronics, these quantum computers, things like that. There's a particular isotope of helium, however, called helium-3, which most of these fusion projects that are trying to find ways to combine atoms and get energy out of it rely upon. And so the moon has a lot of this stuff, which is really good. It's thought that the moon is getting bombarded with this molecule, this atom from the solar wind. Because it doesn't have a magnetosphere to protect it, it ends up on the lunar surface, and we should be able to mine this back. So there's hope that in the long run we'll be able to develop fusion-powered thrusters and so forth that will be able to take us away from there. And there's a lot of hope that helium could play a big role in that. not necessarily the helium that we're running out of on Earth, which is helium-2, but there's also some hope maybe we could transmute helium-3 into helium-2 in some sort of controlled fission. So there's problems, though. It's not going to be super easy to end up on the moon. It's not a very hospitable place, as you might imagine. The surface temperatures they have quite a range of surface temperatures. It can go from minus 280 degrees Fahrenheit all the way up to hundreds of degrees, depending on the time of day, the moon's day, anyways. Radiation is also a big problem. Very thin atmosphere, no magnetic field. You're going to be just getting cooked with all sorts of high energy particles and radiation, gamma rays, X-rays, things that are going to hurt a lot. And so the thought is maybe we dig into different lava tubes. Maybe a lot of the life, the living on the moon is going to be subsurface, which, it brings up a whole other point, which is like, going and exploring space isn't going to be particularly glamorous, especially, even when we get to Mars, right? It's going to be a very long time before we're able to erect anything that looks anything comfortable like what we have on Earth. There's dreams of, we'll talk about Mars next week, but there's dreams of being able to re-establish, or depending on if it had it in the past or not, but establish an atmosphere, be able to grow plants there eventually. I think greenhouse type systems will happen, but the radiation is really a problem, and it will drive us underground. And so the colonists who go and establish these cities are going to be suffering a great deal. It's not going to be a fun walk in the park. And so that's something to think about. It's often, people are often thinking, I'd go to Mars, that sounds fun, but it's going to be several generations before anything approaching fun is part of the experience, I think. There's a lot of really caustic dust on the moon, really fine dust. If you've ever worked on machines or cars or anything like that, you know that getting dust inside of the engine is a complete nightmare. It can very quickly grind down the different working surfaces. And this is going to have to be addressed. It's also not clear how low gravity is going to affect the human body. It doesn't seem like it's good from what we can tell right now. It seems to impair the immune system. You have bone density loss, muscle loss. And so there's a whole astromedicine department that's opening up, which is trying to figure out how we're going to combat these problems, both with medicine and exercise. So we'll have to figure that out. Another thing is, how do we regulate what happens on the moon? There's obviously all these countries that are trying to get out there and get to work on it. I've mostly been talking about the United States program, but there's less transparent projects coming out of competing nations, and there's no agreed upon fashion by which we're going to move forward on the moon, which is a little bit scary. They tried to create a treaty. I believe this was back in the 80s. Don't quote me on that. But a while back, a bunch of the communities came together. The UN was involved. And characteristically, all of the countries that had no chance of getting to the moon signed the treaty, but nobody who was actually going to the moon signed the treaty. So the United States, China, not on the list. Russia, not on the list. And so it's sort of this, it's a bit of a tragedy. We have this moon treaty, but nobody that matters has signed it, and nobody seems interested in getting together and signing anything like that at the moment. So, yeah, Star Wars in the future? I hope not, but it's not totally out of the question. And we're obviously going to have to figure out how to get along on Earth eventually if we're going to get to another star system. But that's another project altogether. Okay, so the early astronomers thought that the moon had continents and oceans. That's what they thought these Maria were. Actually, the word for Maria comes from the word for sea. That's what they thought it was. It wasn't. And very quickly, folks realized that this was not the case once we got some of these more powerful telescopes in the 20th century. This is a picture of a mountain peak on Tycho crater. And so it turns out that unlike Earth, where the mountains are sort of a different substance. They're generally rooted in granite. The hard, brittle parts of the crust are different sort of rock than the magmatic stuff upon which they rest and upon which the seafloor is formed. On the moon, these seas and the mountainous regions are just the same stuff, right? It turns out they're just impact craters. They've been mashed. The thought is that the seas, the Maria, maybe are more volcanic in nature. They're a more fresh sort of basalt. But ultimately, the materials are not that chemically different from one another. And so this turned out not to be the case. And the crust is mostly this rock. It's a silicate. It's called anorthosite. And we find these very good samples of these up there in the highlands, which are these light regions. And this is this plays into the story of the crust. We'll get to that in a minute. Yeah. So the Maria are less cratered than the highlands, which is why folks have come to understand them as being younger. Eventually, once we went there and brought back the samples, we were able to do the radiometric dating, and we did find them to be younger. They're not quite as younger as they should be, given the cratering. And that's a really interesting story I hope that we'll get to here in a moment, because the comparison of these two dates, based on cratering versus based on radiometrics, is a very different story. And so trying to make sense of that is an interesting task. So like I said, originally most of the astronomers believed that the craters were volcanoes. It wasn't until Grove Gilbert in the 1890s pointed out that the lunar craters had these circular floors that were generally below the surrounding plains, and that volcanoes didn't really do that. So, volcanoes, we have a few of them around here, they generally reach up into the sky before you find the craters, and this didn't seem to be the case, and this was the first sign that something else was going on. They couldn't believe that they would be craters because they didn't see anything hitting the moon. And we've seen a few of them actually over the years since then, but this was a hard pill to swallow at first, surprisingly. And the basic way these craters work out is that you have this impact which sends stuff up above it and scatters it, sometimes for hundreds of kilometers, and you get these really interesting streaking patterns as a result of that. But there's a bit of a disconnect here. So here's the thing. There's about 10 times more craters in the highlands, the whitish stuff, than there are on similar areas of the Maria. Okay. So if you work that out and you compare that there's 10 times as many craters there as there are in the Maria, and then you date the Maria versus the highlands, you find the Maria is about 3.5 billion years since that rock was cooled. You find that the highlands are 4.2 billion years old. And the question is, when you calculate the amount of cratering that happens in that span of time, which is something less than 1 billion years, 500 million years or so, you come up with a certain rate at which the cratering forms. So many craters happen every year or something. Actually, not even one every year, but you come up with a certain rate. And so the scientists were very excited. They ran back and crunched the numbers very quickly and tried to extend. They looked at the whole surface of the moon and they said, okay, if the asteroids or the impacts are happening at a rate of so many asteroids per year, how old is the surface of the moon? And they crunched the numbers and they calculated that the moon was 38 billion years old. And then somebody obviously was like, hey, actually, I think this is older than the universe should be. And so they said, well, then I guess all of the impacts happened in the first place a long time ago. This is the conclusion they drew. And this is a really fascinating contradiction to me that I think will elaborate on as we get a bigger, better, and more distant picture, a cosmology about the oldest parts of the universe, because that story is also on the move. There's a lot of talk about the date of the oldest parts of the universe being pushed back. They're finding older stars that are much older than this 13.8 billion year mark. And so if the date for the birth of the universe gets pushed back, maybe this theory will be revisited, because the model that they came up with was that, okay, you have a normal cratering rate today, but in the past, there was like a gazillion craters that were happening at the beginning, because that's what's necessary in order to fit all those 38 billion years into the short time frame that we've allotted for the entire solar system to have been formed. And I think that that's really worth considering, how this interpretation might evolve as our story of how old this place is, because all of the stories we tell, the stories we tell about our whole solar system, they're made in order to be fit into this narrative that the universe is only 13.8, 14 billion years old. If the universe is much older, then these timelines can be extended quite a bit. And this is tricky too, because a lot of the heavy stuff on Earth, the metals, especially the really big metals, are thought to have been incorporated from multiple generations of supernova that have happened. It's not thought that that you can get uranium or even some of the less heavy metals like gold. It's not thought you can get those out of a sun like ours. You need something bigger. You need multiple generations of stars to have lived and died to give the metals that we work on right now. And so this has constrained the timeline necessary to form a star at all, because we should have had several different generations of stars before our own planet was formed. And so the evolution of these timelines is, I think, a really fascinating topic to watch as it changes over the years. And really the expansion of our understanding of how big the universe is has changed radically. I think I've pointed out before, but we thought that the entire universe was just the size of the Milky Way for most of modern astronomy, all the way up into the 20th century. So we couldn't see anything. When you go outside at night, you're not seeing stars that are outside of the Milky Way. All of the stars you see are very close to us. And until they got some of these super powerful telescopes like the Hubble telescope, they weren't even able to see other galaxies. They thought this was it. And so all of these conceptions are constantly on the move. And this will be very interesting to see how it's updated. So great, we have 15 minutes to deal with Mercury, which is fantastic. Mercury looks a lot like the moon, as you can see here. It's a little bit bigger, but very similar surface appearance, equally cratered and pitted. And it also has some regions that, maybe appear like these Maria, a bit darker than others. And one thing that's quite interesting, it's very, very dense. Mercury's density approaches the Earth, and this has led to a bit of understanding about the core dynamics of it. Like I said, Mercury has a little bit of a magnetic field too, which is curious. But Mercury has been a curiosity for a very long time. The Assyrian astronomers were the first people to really make notes of it. This was in the 14th century BC. And they called it the jumping planet, which is quite interesting. They named it Nabu, the Babylonians, after one of their gods in their mythology. And then Ptolemy came along and wrote about it. He thought that you couldn't, if Mercury was there and then it disappeared, they weren't able to see the transit of it across the sun, which is interesting. And so Ptolemy was one of the first people to suggest that maybe it was just too tiny and the sun was just so big, which is actually a rather astute observation. In China, they called Mercury the hour star. The modern Japanese and Vietnamese call it the water star. In Hindu, it was they called it Buddha, which is interesting, which was associated with Wednesday, just like almost all the Western traditions in some way or another associate Wednesday with Mercury, which is fascinating that these different disparate cultures found the same use of it. We think of it, it's been associated with the Norse god Odin or Woden. This was, and in Germanic paganism, they associated it also with Wednesday. The Maya associated it with an owl, which served as a messenger to the underworld. Very different take. But as you can see, Ptolemy wasn't completely off his rocker with this. This is actually the transit of Mercury across the sun. And there's a sunspot in the middle, sort of, but off to the lower left-hand corner, you can see Mercury as it makes its way up across the sun. It's very, very small and very difficult to locate without telescopes, which is interesting because several reports were made of a transit of Mercury, especially in medieval times during the 12th century in Islam. There was a lot of great astronomy going on. A lot of great mathematics were developed there. And there was a report of Mercury and or Venus being coming across going across the sun. Most people have come back and argued that they were actually just seeing sunspots, which you can see look more, they look kind of similar. But sunspots are a lot easier to see from Earth. And so they must have been using some sort of projection system to do this. Today, if we want to look at the sun, you just use a telescope, and instead of sticking your eye in the eyepiece, you can project it onto like a white screen in the background, which is pretty cool. And I hope we can do that at some point. I think that our astronomy night's not going to happen until next semester, unfortunately, but I'll try to email all of you guys when we pull that off. It looks like the weather has taken a turn for the worst on us. So, now, this is what I was trying to get at a little bit earlier. I hinted at the fact that Mercury might look a lot like the moon, but it's mostly core. And how do we know that? Well, mainly because it's so dense. It's and the density can be calculated obviously by the size and the gravity, which gives us the mass. Now, Mercury is so dense that the only way to achieve that density would be to essentially make the thing entirely out of core. Now, this is in some sense problematic because Mercury does have a magnetic field, but it's extremely weak, like 1% of the Earth's magnetic field. And yet, the core is enormous and it's very close to the surface. And so, again, we run into this issue of, okay, if the moon and Mercury formed and everything else in the solar system formed at the same time, why has the moon cooled sufficiently to essentially leave no liquid core such that there's no magnetic presence, and Mercury, on the other hand, has remained active after all these years? And the thought is, like, Mercury has let me see if I have a picture of this. I guess not. So Mercury has a very highly eccentric orbit. It's very close to the sun, so it's thought that as it swings into the sun, there's a lot of sloshing going on, essentially. There's a lot of tidal effects in its interior, and that this friction of the pull on the interior has allowed it to remain liquid, which can help the magnetic field persist. It's also worth noting that since the core takes up most of the volume of Mercury, there isn't much insulation on the outside, right? And so this might help. It's also possible that since it's so dense, it might have a really,
Yeah, sorry.
Mhm.
Sorry.
You're good.
It's silly question, but so we know it's like mostly core with its density, but how do we know it's all liquid all the way through?
Yeah. That's what I'm getting at. Is this all sort of it's all indirect assumptions, right? We have to. Our model for how magnetic fields are formed relies upon liquids. There has to be this liquid component in order to generate those eddy currents that allow us to get the magnetic field out of it. And so the assumption is that, well, the only way to generate a magnetic field is to have a liquid core, so there must be one. But the density leaves us to believe that there must be a pretty big solid core also. Now, the solid core is interesting because, like I tried to convey in the lecture on magnetism, that the solid core, when you stick a big piece of iron or nickel in the center of an electromagnet, it allows the magnet to persist long after the current has dissipated. So you can make a permanent magnet out of the central region that can persist. And so maybe that has something to do as well with why Mercury is able to keep this magnet going after all of these years. There's also different theories entertained about Mercury was perhaps impacted with something very similar to the moon's formation. We talked about the Theia hypothesis for the giant collision that may have formed the Earth. Well, sure. May have formed the moon, like some big planet came and smashed into it. Maybe something happened similarly with Mercury, maybe not that long ago, because maybe that contributed to the liquid character of it as well. But it's certainly an anomalous situation. And actually, there's some other really interesting things, like Mercury and the moon both have the least axial tilt of any of the bodies in the solar system, which is quite interesting. They're very well aligned with the sun and in the ecliptic with regard to just their tilt. So they're like puzzle pieces. You learn about these things that are similar about planets. You learn about the things that are different, and you try to come up with a story of what might have happened to lead us to that point. And these ones in particular, the similarities and differences between Mercury are really unfinished stories right now. And I think we'll see something interesting coming in the future. If it turns out the moon is 38 billion years old, that leaves a long time for Mercury to have developed, maybe to have evolved from something with a much thicker crust and something that looked more close to, say the Earth or Venus or Mars. Another problem with this too is we try to understand, why does Venus not have a magnetic field, right? It also, if you go by this density argument, it should have a liquid portion as well, and a solid portion. I actually do have a picture of this. So here's a comparison of all our terrestrials. We'll be doing the terrestrials all next week too. So, Venus should have a portion, and honestly, the insulation layer, the mantle, isn't that different than Earth on Venus. And so this is another conundrum, because the way that we explain right now why Venus doesn't have a magnetic field is because there's no way for this convection to take place, because there's no cracks in the surface of Venus like there are on Earth that allow for this heat exchange. And this is a nice story, but it's not totally clear. Again, on Mercury, Mercury doesn't have these tectonic cracks either, right? But Mercury has a magnetic field, and so this is another piece of the story which is slightly out of line and requires, I think, a great deal of thought. The insulation is different. I'm not sure to what degree that, obviously you can magnetically insulate metals on Earth. We do this. There's different ways of doing this with copper and so forth to, protect things usually from radio transmissions and so forth. So it's possible that the very thin insulation on Mercury could be playing into the differences that we see here. But all of these rocks are more or less laid out the same way. And so the similarities are pretty well apparent, but the subtlety of the differences is what's going to come into explaining why we have such very different outcomes on all of these planets. It would be very easy to, if Venus didn't exist, this would all be very easy to explain, right? Okay, well, Mars has, Mercury has a little bit of a magnetic field. It's very old, and Earth happens to be in this perfect region, and then Mars is dead and has no magnetic field, and so we're just in this Goldilocks region. But Venus kind of throws a kink into this whole pattern because it's in between the two, right? Venus is weird too because it's not. It rotates the wrong direction, which is very strange. Venus. There's different theories about Venus being captured into its orbit or having moved orbits at some point, which is interesting. We'll deal with Venus though next week. Here's those axial tilts that I was talking about. So you can see the moon's tilted at 1.5 degrees, and Mercury is only at 0.1, which is really, really interesting. To the eye, they look very, very ancient, these two, Mercury and the moon, which is fascinating compared to everybody else. This is kind of interesting. The rotation or the orbit of Mercury with respect to the sun, it's tidally locked in a fashion that has this 3-to-2 perfect spin orbit resonance. So that means that it rotates on its axis 3 times for every 2 revolutions it makes around the sun. This is actually in music called a perfect fifth, which is just a lovely coincidence that happens. And so Mercury rotates so slow that a day actually lasts about 2 Mercury years, which is something like 87 days for us. So the day is longer than the year, which is very, very strange. I guess the last thing I want to say is Mercury is probably not that useful to us as a planet because it's just wildly inhospitable. Since it rotates so slow, one side of it's always getting cooked, the other side's very cold, the temperature swings are unbelievable. It's like the surface gets up to 430 degrees Celsius at noon, and then after sunset it plunges down to minus 170. And so I don't think that we'll be going out there and walking around on it anytime soon. But let's stop there, and we'll do Mars and Venus next week. And let me know if you have questions, thoughts, ideas. We'll see you next week. Have a good weekend.